Okay, so this is part 4, and it is going to be focusing on device offloading. The idea here is that we're going to start compiling GPUs. The first thing you're going to notice in the lab is that I changed from GCC to CLAN, just because I'm more familiar with the LLVM implementation of OpenMP offloading, and because I know that I can make modifications if need be for this to be able to work well. Again, thanks to Chameleon for providing us with the compute resources. Thanks for Aurelio for setting up the compute resources to what they are right now. Before I start, can I just get some hands up or something, just so I know that you guys are listening to me, or it's quite difficult if I don't see people. Thank you. Thank you. Thanks, guys. Okay, so what are we going to see here? We're going to see that we went from a model where we only had threads, where we only had a CPU, and where the CPU had a shared memory, to a model that we are going to call the offloading model, that has something that we refer to as an accelerator. An accelerator is a second device in our system that has different compute capabilities and that has the ability to execute certain code faster than regular CPUs, just by the fact that it has specialized compute capabilities. Okay, so in order to do this, we have to understand what the target directive is. We want to understand how the memory between the CPU and the device work, and then we are just going to focus on the GPGPUs for 2 reasons. The first one, they are widely available right now. They are the device that most of the people use, and it is the most mature implementation of OpenMP. OpenMP offloading model is not only for GPUs, but it is right now mostly implemented in GPUs. There are works that have been done to do FPGAs, to do other device accelerators, but most of the people right now are using it for GPUs. Okay, so we're going to talk about parallelism generation in GPU, memory management in GPU, and a little bit of synchronization aspects of GPUs. Okay, so the offloading model. What happens is that when you start looking at the history that I was telling earlier about computation, the beginning of the 2000s was the end of sequential computing and the beginning of parallel computing, commodity computing, meaning that it was available by many vendors and that it was easy for you to just go and get a processor that had more than one core. Then as we progress, we realize that there are other ways that we can build architectures that for either specific programs or a specific set of programs, it makes sense to build, to compute or to execute the code in a different way. So we start calling these accelerators. And when we talk about heterogeneous computing, it's because we went from a homogeneous CPU on the computational model to a heterogeneous model where we had more than one device, and each of the devices had a different name and a different set of capabilities on how they compute, right? So some example of this are Google TPU, which is the image that we have on the right. So Google TPU is an accelerator that is really good at doing neural networks. You can go and buy execution time in Google, and they have a way of programming the Google GPUs that most likely is not going to be similar to OpenMP. And we have this set of devices that are GPUs that are really common because most of the computers will need one to use it for displaying videos or playing games or things like that, that have started to become more and more popular for computation because they have the ability to execute a lot of instructions at the same time. So what they do is they create a lot of little cores that are way more lightweight than the traditional CPU cores, that are slower than the traditional CPU cores, but because we have so many of them, we are able to execute the same operations on a lot of data at the same time, so we increase the throughput. So the GPUs, the point of having GPUs is that we can increase the throughput of computation, while the point of having CPUs is that the latency of the computation is low, meaning from the moment I start executing the code till the moment that the code finishes execution in the sequential execution order, we want that to be as short as possible. While in the GPUs, we don't care if the execution of a single thread is slow, but we are doing so many of them that we end up progressing in computation a lot. Right, so how do we program the systems? There are many ways. There are many levels of abstractions. that we can use to program the systems. If you guys were here for the Monday meeting by Sarah and Gabriel, they discussed possibilities of using already existing libraries in the system. They discussed the possibility of using CUDA, which is a low-level programming model for NVIDIA GPUs. Or there are other ways that I will discuss in a second. But what is important here is that we have a developer that has to now not only understand how to create workers, but also where to create workers and how to coordinate workers from different devices. The idea here is to be able to have a single source code that we can later on target to different architectures. That is kind of like the dream of heterogeneous computation. And the idea of OpenMP is that it allows us to achieve somewhat achieve that dream, even though that is not, it is still something that is work in progress in terms of research and whatnot. Okay. So what do we do? Is that on the top we have high-level applications. A lot of you guys have been working on high-level applications. Those high-level applications most likely are going to be using libraries or being using OpenMP or other programming models that are a little bit more low-level. At the bottom, we have the hardware. Each of them has a different set of low-level programming capabilities. So in the case of CPUs, we used to, you probably are familiar with the concept of assembly code, that is the basic instructions of the CPU and is as close to the CPU as I can get in terms of assigning instructions to the CPU. For GPUs, if we are talking about NVIDIA GPUs, we can say PTX. PTX is the assembly code of GPUs for NVIDIA GPUs. And if we were using TPUs, then most likely there is going to be a set of assembly code that you can run and execute in the Google TPUs. As we go further up in the stack, we start seeing that each of the vendors have already created a set of libraries and a set of programming languages or programming tools that allows us to map the execution of code into that particular architecture. So CUDA, for example, is a programming language created by NVIDIA such that you were able to create code that will map, C code that will map into the execution of the GPU. But then as you go closer to the application, you start noticing that you need a set of operations that are higher level domain specific operations. So for example, I am working on matrix multiplication. I have a library that uses matrix multiplication. Or I am working on neural networks. I can do cuDNN or something like that. That is a CUDA library for neural networks. So there are all these high level set of operations that I can find in libraries and that I can just plug in and play into my application. And then those libraries will be able to use the device that I'm trying to do. So as you see, as you go higher up and higher up, you end up getting closer to the programming languages that support the low level, the architecture specific and low level tools. But also there are applications that already adopted some of these low level tools, either through the use of programming languages or through the use of the libraries themselves. So what is OpenMP target offloading? It is set in between the different libraries because there is support to providing connections in between libraries of third parties and connections with the programming languages. And it is on the programming languages because as we saw, it is possible to actually use C and C++ and annotate C and C++ to be able to execute code. And what we are going to see is that we are able to do that for the GPU as well. Okay, so in the offloading model, we have this idea of a host-centric execution model. Oh, wait, we have a comment here. Does OpenMP implement some kind of virtual machine to have an intermediate interface to all of these low-level assembly languages? It doesn't, it is not really a virtual machine. What happens is that the compiler or compilers have an already existing interface in, for example, C. So if you take, for example, CUDA, CUDA has what is called the CUDA runtime system. The CUDA runtime system is written in C. Now, LLVM will support creating PTX code directly from C code. So you take C code and you lower it down to PTX. Once you have PTX, you can give it to the CUDA compiler to be able to generate the binary of the GPU. So the low-level CUDA compiler is called QBin, and what you do is you give the PTX to QBin, and it gives back. Sorry, it's not called QBin. It's called QBin is the name of the file that gets at the end. Yeah, it escapes my mind right now. So you get the PTX, which is the low-level programming language of the CUDA device, and you provide this PTX to that compiler, and that generates the QBIN, and then later on you take that QBIN and use the CUDA runtime system in C. That is all handled by the runtime system in the OpenMP implementation to be able to say, go and execute this particular code in the GPU. Okay. Does every compiler agrees on the intermediate representation while compiling OpenMP? No, they do not. They used to have OpenMP runtimes that were compatible with each other, so you would be able to create a OpenMP runtime for LLVM and then run it on GCC programs. But with device offloading that has been so hectic, that is not the case anymore. How OpenMP compiler will compete with other HPC APIs like OpenCL or newer SQL and guarantee core cross execution with an IR like SPRB. That is the dream, right? So I work a lot with OpenMP, but I don't think that there are many elements in OpenMP that make sense. And one of them is that in terms of parallelism, each of these frameworks that you are describing, they tend to have their own runtime. And when you try to connect the two runtimes together, they tend to collide in the execution. And so there are many cases where if you try to use a library that uses OpenMP next to a library that handles their own parallelism using pthreads, there is going to be some sacrifice in the performance by just having the two runtimes trying to think that they are the owners of the program. Now, that being said, OpenCL, for example, can be like all these high-level OpenCL, SQL programming languages can be lowered down to OpenMP runtime function codes. So there are work by other people that have taken programs that are not written in OpenMP, and they still use the OpenMP runtime system to try to target the OpenMP, the accelerator devices. So these runtime systems becomes the closest IR, the closest abstraction that you get to be able to connect the two worlds. But it is absolutely true that it's not as simple as just saying so. One thing that they are working on OpenMP is that you are able to create multiple, you target the same code, targets multiple architectures. So you can get SPIR-V for Intel architectures, then you can get PTX for NVIDIA architectures, and then you can get HEAP for AMD architectures. And all of them can live in the same binary. And then the runtime, depending on which architecture it says during runtime, it will decide which code is going to be executing at the end of the day. Okay, does that make sense, guys? I have a slide somewhere in one slide deck that I created at some point that I say too many chefs in the kitchen with respect to having too many runtime libraries trying to think that they are the owners of the system, and that is definitely a problem. Julian, were you going to say something?
No, nothing. Only yes.
Excellent. Okay. So host-centric execution model, we have the CPU and we are going to call it a host. A host, because it's going to be the one that communicates with the operating system, is going to be the one that starts the execution of the program. That execution is going to most likely going to be sequential, the same way that we were discussing about the 4G model before. The host is going to have an interconnection to a set of devices that are also part of the system, but they are two independent execution environments. So the execution of the host is going to begin. The execution will begin with a host region. The host region will eventually result into a GPU region or a device region that will offload the execution of that particular segment of code into the GPU. Then we can go back to a host region that can later on offload execution to a TPU region. Or we can even have the overlapping of execution of host, GPU, TPU, and other accelerators by means of doing, for example, a parallel region, and within the parallel region, creating target regions, or by means of using tasking, which I know I'm not discussing in this particular tutorial, but you can create tasks that are able to coordinate and communicate with each other in a dependence graph manner, such that you can execute code in different parts of the system with different architectures, each of them. So the idea of the host-centric model is that the execution begins in the host is coordinating the execution throughout the whole program. but we are offloading execution into the devices all the way until the end of the program. Okay, so a host-centric model is a model where the host becomes like the owner of the computation and the coordination of the computation. Personally, I don't think that is all the way correct. I think that from the perspective of the three questions that I said earlier, worker creation, communication between workers, and work assignment, it makes sense to think of the host as a scalar unit that is able to coordinate execution of code by means of creating all these target regions or creating all these parallel regions. So what I imagine the host being is this coordinator of work that will determine where the code is going to be executing, when the communication happens, and it will be able to connect the different blocks of the program in such a way that they respect the dependencies of the execution. But that being said, OpenMP as it is right now sees the host and its complete set of threads and its complete set of OpenMP parallel regions as a whole unit, right? So they don't distinguish between the scalar unit and the computational units. They only say host as the CPU and that's it. So you are able to utilize the host and the GPU at the same time, but you need to understand that the host is also in charge of the coordination as well as creating the execution of the code in the CPU. A lot of applications, they end up only doing the GPU, and so you end up losing the computational power of the CPU. Okay, so the target directive is just a directive that says to the compiler, this region of code has to be executed into a target. So OpenMP is responsible to translate, communicate, calls, and issues to an accelerator. Absolutely right, Isaac. OpenMP is in charge of, the compiler will translate the code in this, for example, in the code that I have in the slide right now, the region in between the pragma MP target beginning and end, like these two brackets, has to be translated to the device code, right? So this has to be translated to PTX, that later on has to be translated to QBIN in the case of NVIDIA. Then the fact that I have this construct that is an executable construct means that there is an offloading event. That offloading event is actually an event that happens during the execution, that is a function call that communicates with CUDA runtime that says, here is the function that I'm trying to execute. Those offloading works on demand, JIT, or at compile time. There are people working on that, in particular, Joseph Hoover from Oak Ridge National Lab. He, in LLVM, he's working on trying to make the linking aspects of OpenMP a little bit better, such that you can do JIT by leaving the device region in LLVM-IR and then using that LLVM-IR as your intermediate representation that you can later on lower to whatever device. So that is work in progress. It is an option that is going to come eventually, okay? And if you think of other devices, Intel, for example, has thought about this before, and I think they had some implementations that were thinking of JIT. For those that don't understand, JIT is just-in-time compilation. That is when you do not compile your code prior to the execution, but at the moment of execution, you decide how to compile your code. The advantage of JIT is that during the execution, you may have information about variables that you thought were variables, and now they are constant during the execution. So you can make optimizations that fit the exact values that you get during the execution of the code. So that is just a technique in compilation for that. Is that good, Isaac? Isaac? Okay, I'm gonna take that as a yes. So the target directive is, as we were doing, yeah, no worries, anytime. The target directive, as we were saying before, is an executable directive that will outline a part of the code, will create the code in the device, in the particular device architecture, and whenever the execution of this code reaches this pragma MP target, you do an offloading operation that will send the piece of code into the device, and then at the end of the execution of that code, you will return from the offloading operation and you will continue the execution of the host. Right? Hence the whole idea of the offloading model. If you see, you're kind of like sending work to do somewhere else. And so if, in the words of the three questions that I always ask, I am specifying that there are going to be some workers in the device, and I am assigning the work that those devices are going to be doing by performing an offloading operation. Okay, so the target directives creates the offload region. The offload region is translated into the accelerator, and then it sends the data back. It sends the code to the accelerator and then back when the code finishes. Notice that I did not express any parallelism so far. So it is just a matter of saying, it is just a way of saying this code is going to be executed in the accelerator, but it is not a way of saying how I am going to express parallelism within the accelerator. That comes after, okay? So the other thing is that CPUs and GPUs, they tend to have different memory spaces. So in the CPU side, we are all familiar with the DRAM, but in the GPU side, there is also some DRAM, usually referred to as the GDDR, which is graphics DDR, which tends to be much faster. It tends to be much higher bandwidth, and it tends to be much feasible for the fact that in the GPU, I have a lot of workers trying to access the device at the same time. So because we have two different memory regions, more often than not, our coordination of work is going to also include data movement in between the CPU and the GPU, okay? So there is this new concept that I need to consider when I do target offloading, that is the fact that I need to move data back and forth in between the CPU and the GPU. There are mechanisms that will do that for you. I will describe them, but I will not cover them during the lab, because I want you to really understand the data movement operation. So as I said, device memory, completely independent from DRAM memory. Compute capabilities of the accelerator, completely independent from CPU capabilities or from compute capabilities of the CPU. And that also includes registers, and that also includes the cache. So we just took the problem that we were having earlier to another level, with the caveat here that we are going to be most likely doing manual operations to perform memory copies in between the CPU and the GPU, or the CPU and the accelerator device that we have on the other side. So here is what is important to notice is that by default, GPU and CPU memory locations are going to be completely independent from each other. So in the host memory, I may have a variable int x, and I may be able to access that variable int x from the CPU. But if I want to try to access that variable int x from the accelerator, by default, if I am not using shared memory, it will not allow me to do so. And the accelerator code will actually fail, and you will get the typical segmentation fault that we all love when we program code, right? So what we have to do is we have to actually manually perform a copy memory operation such that we can create the X variable in the accelerator's memory, and then later on we can access that memory from the accelerator. And so there is this coordination that has to happen in between the host memory and the CPU, the host memory and the accelerator's memory, that has to do with copy memory back and forth in between one and the other. Okay, so the trick here is to, similar to what privatization looked like, is to know that whenever we define a target region, there is going to be a new data environment in the accelerator, and that I may need to make copies of data into the target region, such that each target region is similar to what we did with privatization, in the sense that each of the variables that I put in the target region may or may not have a different memory location. Now, here is the trick, that we do not always deal with data structure or with variables that are integers, doubles. We sometimes deal with data structures that are linked lists, graphs, and trees, and like really complex data structures. So by default, OpenMP is going to be really good at making memory copies of contiguous memory array. And I will discuss this later on in the slides. But there are ways that you can actually specify how to actually map different data structures that are not linear in memory. It's just a little bit more complicated. And I'm not going to be covering the most complex aspects of that is called a declare mapper, but I'll give you an insight of what it actually does. Okay, the name that is given to the fact that I'm making memory copies in between the CPU and the GPU, or the device, is mapping. So mapping is taking a variable that has a name in the host memory and put it into an accelerator memory. I can map to, meaning copying the data from the host to an accelerator. I can map from, meaning copying the data from the accelerator to the host. I can say, just do the allocation, similar to what happened when we did the privatization of variables. Just give me the memory location. I don't care what the result, I don't care what the value of the memory location is at the beginning. Don't worry, I will override it. I will do something about it. But for now, just give me the memory location. And if I do an allocation, we all know that if we allocate memory, we always need to deallocate it. And there is this process of deallocation. Okay. So again, in this case, we are just copying memory back and forth. That also means that you're going to get pointers here that are different to here, similar to what we saw in lab 1. Okay. There are two ways that we can do memory management. The first one is called structured memory management, and the second one is unstructured memory management. In the structured memory management, we are creating a data region that has a beginning and an end. And so I cannot do structural memory management in between two different functions because I have to enclose my memory region in between an opening bracket and a closed bracket. So I cannot open a bracket in one function and close the bracket in another function, right? So I know that at the beginning of the data region, I'm going to have some copies from the host to the device or allocations to the device. And at the end of the data region, I'm going to have some copies from the device to the host or the deallocation of memory in the device. Target regions by default have structured memory management. By just saying target or pragma OMP target, I am creating a target, a data region or a data environment in the device that is going to have all the properties that I just described before. But in the target region, we are connecting the memory movement with the computation, right? At the beginning of the target region, you may have memory movement or data allocation. Then during the computation, you will use those newly created data regions. And then at the end of the target region, you will have data copies copied back from there. However, memory movements tend to be really costly. So there is a possibility of having a target data regions that are only focusing on the mapping of variables and not on the computation of variables. And I will have examples in a second. In an unstructured memory management world, what I do is I move memory on demand. I'm going to say at this particular point in the code, I'm going to take this particular variable and I want to send it over there. I can do target enter data, target exit data. I will explain it in a second. I can do target data updates, or I can do manually doing the OMP target name copy. Okay, so let's talk about structured data movement. So going back to the example that we had before, the idea here is that every reference that I get inside of the code has to have some corresponding memory operations. So in this case, I have an array of integers of 10 elements, and I'm going to just print the first element here. There has to be some memory copies in between the host and the device at the beginning and at the end of the region. Here, what I'm going to say here is that there are going to be some implicit memory mechanisms that happens to be mapped, or that happens to be directly related to the type of the variable and the fact that we know or we do not know the size of the memory location that we are trying to access. But what is important here to notice is that in a target region, I do have some memory copy into the device and memory copy out of the device. Okay, really, really important. OMP target is absolutely different to OMP target data. OMP target executes code in the device, while OMP target data only does the data region and only starts at the beginning of the OMP target data, I copy data or allocate data. At the end of the OMP target data, I copy data back to the host, or I deallocate data. Okay, so in this case, if I say I'm printing a value in the host, right? Like I'm in the host here. This is my host execution, and I start a pragma OMP target data map X. This does not say anything about the fact that the code that is within that target data region is going to be executed in the GPU. It is not. This region inside is going to be executed in the host. Okay, so I am only creating the data move to the host and creating the data move back, sorry, to the device and creating the data move back to the host. Is this clear? I think it's important because people tend to confuse a lot in between target regions and target data regions. So they do not execute target data regions. The code within the target data regions does not execute in the device unless I have a target region inside of that code. All right. So there is this idea that there are variables that are going to be implicitly mapped. The trick here is to know for a specific variable if the compiler is going to be able or not to determine what the size of that variable is. And there are two types of implicit mapping. One that is done to the scalar variables. Scalars are integer, floats, doubles, all those functions or all those data types that you basically use, like the basic data types. Every time you have a scalar variable inside of a target region, and that scalar variable is a standalone, it's not, for example, part of a class or part of a struct, right? It's just a single variable located in the stack, for example. Then there is going to be a first private, an implicit first private clause inside of the target region. So that means that if I modify my variable within the target region, that modified variable is not going to be copied back into the host. Okay, so that applies for ints, that applies for doubles, for shorts, for cars, for floats, for longs, you name it. Okay, all these basic data types. Then there is an implicit data mapping for non-scalar variables, right? So any variable that is not of the basic type, for example, a struct or a class, is going to have by default a mapping of to from of that particular variable. Something here to notice, and it's going to be important in a second, is that pointers, and so if I say my struct pointer and my struct, those two are completely different data types. So a pointer, as Carlos said earlier, is just a number to a memory address of the type my struct, while a my struct is the actual object that contains the values in the struct. So in this case, if I have an struct that is called my struct and that is named X, if I go and modify that variable into the target region, because this is not a scalar value, it's going to be implicitly mapped as to from, and it's going to be modified back into the host. Is this too complicated? Are there any questions? Okay, I'll continue. So the other thing is that if I have arrays that I do know that the compiler knows the size of those arrays at the moment of entering the region, it's also going to be mapped as to from, okay? Ignore this 0.3 for now. I will explain what that means in a second, but that only means that we are copying all the 3 elements that we have in that array. In this case, it's an array of ints that has 3 elements. If I modify one of those elements, I'm going to see that value back into the host, okay? So again, implicit data mapping just says that if I have a variable of the type X or Y, what happens to that variable? If it is an array and we know the size of the array, then it is copied. Is there a way to tell the program not to map those structures? Yes, explicit data mapping, okay? Another implicit data mapping is what happens with pointers. And this, you have to be absolutely careful. I have been saying over and over, as long as the compiler understands what is the size of the data that you are trying to copy. Here is the problem with pointers. Pointers are also used to represent arrays. But how do you know from the perspective of a pointer how big your array is? It can be 1 or it can be 100. So the compiler, from the pointer perspective, it doesn't really know how much data you want to copy. So by default, it is mapped to from, but it is mapped to from without copying any data whatsoever. And what it does is just translating the pointer from the host pointer to the device pointer. And I will have an example in a second. So to from acts from practical effects as passing by reference. As passing by reference. I don't think it does, because when you pass by reference, you do get the possibility of modifying the original. I guess, yeah, from the perspective that when you get back from the target region, you're going to modify the original value, yes. So it is as passing by reference. It's just that in reality, our pointers are going to be completely different from each other. So because the pointers are completely different, then if you modify, if you think about, like, I don't know, capturing the pointer into a function and relying on that pointer to later on do something in the CPU, that is not going to work. Okay. But yeah, I see what you mean, and yes, the data will be modified when you get back. Okay, you can modify the default behavior, right? You can say, I do not want this scalar value to be mapped as first private, but I want all the scalars to be mapped as to from, and that is what the clause default map allows you to do. Again, I'm giving you a lot of hints of what kind of things you can find in OpenMP, but also try to understand that my first intention here is to give you the idea of how we actually program in OpenMP. So there are going to be any more number of clauses that I'm not going to be covering here, but you can start learning from what I'm trying to give you here. So in this case, if you use the default map, you specify what type, so to from, and you specify the type of variable that you are trying to change the default map behavior, then you are able to make, for example, scalar values be mapped to from by default, right? So you don't have to go and map each scalar variable at a time. Okay. A note on data types on memory. I know a lot of people, especially if you are used to programming in Python and higher level programming languages, you don't think so much about how data is represented in memory. But this becomes super important when you are working on GPUs, because now you are responsible of doing memory copies, and those memory copies are going to be referencing a region of memory, right? So every single data type on memory has a region of memory that is going to be utilized. The typical example, an integer is going to be of size 4. There are some architectures when integers can be size 8, but let's assume for now that integers are of size 4. Right, so when I try to figure out what is the size of my variable, I know that it will start in a particular memory location. So if I do %x, I will get this value here, right? And then from that particular memory location, I'm going to be using 4 bytes. That is why it is important to have a data type, because the data type is telling me how big my memory allocation is and how do I interpret the different bits in my value. Okay. Then, if I have an array of integers, what I do have is one integer, one after the other, right? So when I say integer x array of 3, what I have is 3 4-byte numbers that are going to be, each of them is going to be representing an integer. So when I want to copy an array of integers, I copy from this memory location here till this memory location here, because I know the size of an integer is 4, and I know I have 3 elements, so I just need to copy 3 elements, and that I get these 12 elements that I'm going to be copying. So the size of your memory copy is directly represented by the size of your data type and the size of the elements that you want to copy if in the case of an array. I will explain that in a second. Bear with me. Okay, the next one is there you go. A pointer. So pointers are tricky. Again, do not mix pointers with the base data type of the pointer. So an int pointer is absolutely different to an int. An int pointer, for example, in a 64-bit architecture is going to be of size 8. The value that you get from that pointer, the numbers that are written in that pointer, represents another memory location. That is where the actual number is, right? So a pointer is just that connection in between one memory location that contains that the content of that memory location is a number that represents an address. And when you follow the pointer, you are accessing that address that is contained within this memory location by dereferencing the pointer and reaching out the actual value that you get. So in this case, the integer is in the yellow part, but the pointer, which is of size 8, is in the blue part. Okay. When we have structs, the compiler is going to be organizing the content of the struct in a contiguous manner. It means the car here is going to be, so cars, just to give a little bit more information, cars are often of size 1 byte, right? So this is a car, this is another car, this is another card, and this is another card. Because I have four of them, one after the other, okay? And then I have an int, which I know is size 4, so this is my int. So structs and classes, they are often located in memory in a contiguous manner, one after the other. There is something called padding that some compilers do to guarantee alignment such that the execution of the code is more efficient because the memory accesses are aligned to that particular memory location. Do not worry about it. It just means that if I were to do, for example, a card 1 here and an int after that, it is likely that my size of the structure is still going to be 8. You can play with this by yourself in any C++ compiler or C compiler, but it is just important to understand that when we talk about structures, we are also talking about memory regions that are contiguous. And this is important because memory copies often operate on contiguous memory regions. Okay. Then we have, oh, okay, so yeah, size of card is 1. Then size of my string dot my card is 4 because it's 4 elements. Then size of int is 4. That is how I get the 8. Okay. Then we have arrays of structs, right? So we had the my struct before. I can create arrays of structs, and since I know that each struct is going to be 8, I get 16 because, oh my God, get 16 because this is my first element in the array, and this is my second element in the array. So in total, I get 16 elements. 2, which is this 2 here, times 8, which is the size of my str. Okay. Is this clear? Or is it super confusing and super low level for you, or what do you think? All good. Excellent. Thank you, Diego. Thank you, Rafa. Thank you, Kevin. Question. If you do size of my struct or my card, does it actually give 4 because the array contains 4 bytes, or does it give 8 because my struct or my card is technically the pointer to array of the stack? In this case, I'm gonna here saying that it's going to give you 4 because it's an array with a static memory size. So when you try to do this a pointer, what you do is you make this card 8, right? So you allocate eight elements for the pointer, and then later on you have to do a memory allocation to a different region that contains the four cards, right? So in that case, you do get the 8 plus the 4 of the ints. But because we are saying that this is of size 4 statically, the compiler uses this to allocate the cards right inside of the struct. So there is no dereferences in between one and the other. So in that case, it shouldn't give you, I'll make the test while you guys do the lab, but it shouldn't give you 8. I'll make the test, right? Because it is a good question. It's absolutely a good question. Yeah. Thanks, Des. Next. Okay, so here, what is important is data is copied based on the types and the size. So when I do a memory mapping, what I'm doing is copying that contiguous memory region into like same memory region. I'm just kind of like copying that and putting it into the other one. Computers don't really understand memory types. Memory types are something that is part of the compiler and part of the programming language. A memory type is saying how do you structure the memory in the actual physical memory? How do you put the values one after the other? In the computer, all of the reads and writes are kind of like numbers. They just get numbers from the memory and operate on those numbers regardless of what the memory type is. So because of that, memory copies in between host and device are somewhat like that. They just need how much memory you are going to copy and from which is beginning or from which point in the memory you're going to start copying. Okay. So in this case, when we are mapping something like an integer of type X, and we have the host memory here in the top part, right? Notice that the addresses in the host memory are different to the addresses in the device memory. And so when I do the memory copy, what I'm doing in the map2 is I am allocating a memory region in the device memory that has a different address associated to it, and I'm copying the value of this, in this case of the 2, I am copying the value of this memory region and putting it into this other memory region, okay? When I am doing a copy of an array, I am copying from the beginning of the array into a device memory, right? I am sending the data from this memory region to that memory region, and both of them are going to have different pointers associated to it, okay? So as you notice here, and as I said earlier, there is this weird notation that I have with the colon, right? A number below the colon and before the colon, and a number after the colon. That is what is referred to as array sections notation, right? So what the heck is this thing that you're writing there? In reality, what I'm doing is I'm specifying a base operation, right? A base memory location, a lower bound from that base memory location, a length starting from that lower bound, and a stride starting from the so you start from the lower bound, you take as many elements as the length says, and you stride the axis by the stride axis. Just to say something here, stride is currently not supported by any compiler. It is part of 5.1 or 5.2. So it is there, but it hasn't been really implemented in. So I'm not going to be discussing that much the stride axis, okay? Okay, so if I have this, what happens is that if I have something like this, 2, 3, 3, what I'm doing is I have a pointer, right? The pointer is X here. The pointer is allocated in A1, but the pointer is pointing to 0xAE, which is this one here. I am saying that I'm going to take 2 elements, right? This is an array of card. That means that each element is going to be 1 byte. So from here, I'm going to count 2, 1, 2. I'm going to take 3 elements, and each element is going to be strided by 3. So 1, 2, 3, and 1, 2, 3. So I get this element, I get this element, and I get this element. Okay. So it looks like base, lower bound, stride, and length, which is 3 elements from there. Okay. Again, stride as of June of 2022 hasn't been implemented in many compilers. So most likely you are going to only see lower bound, and length. Okay. Okay. So how variables are mapped to the device? When you have pointers, right? What you have is the address of the original pointer, and when you try to map the variable, what you do is you copy that region of memory into the device, nothing more and nothing less, right? So for example, in this case, we are not copying these elements here, and we are not copying these elements here, just these elements here. This is super useful when you have multiple devices, because that means that you can distribute your data across the different devices. Okay. That is memory mapping. Let me clear my screen. There you go. Okay, so what happens when I have the data map? What I'm doing is I'm specifying how to move those memory operations in between one and the other. Let's try to understand this on the left, right? So I have a data map of type alloc of the array Y, which is this one here, and I'm using column, which means by default start from 0 and go all the way to the length. And because the length is known, then it will be allocating all of these elements. I have a map to from Z is a pointer, and I'm going to go from the 0 position 10 elements, right? So I'm going to take 10 elements of this array, and I'm going to copy them over because I have a 2. I have a map to from of K, right? K is an integer, right? So it is an integer. I just allocate the variable of K in the device, and then I copy the values from the host to the device. And then at the end of the target region, I copy from the device to the host. And I have an array of structs, right? That is, this is the struct, this is the array of structs, and I'm going to be allocating from the beginning of the array, skipping the first element, starting from the element 1, is 0, 1, 2, right? So starting from the element 1, and I'm only going to be copying 1 element, okay? So how does this look? We have X is first private because I never mentioned it here. So it is implicitly allocated as first private. S is also implicitly allocated as as to from, map to from, right? Y is only allocated, so I don't copy the data over there. Z is map and copy the data of 10 elements starting from the beginning. S is implicitly allocated, and SA is map only a single element into the device. Okay. So map reference, counter, and present test. So far so good. I know this is a lot. I go over all of the elements again in the lab, so I really hope that this makes it a little bit more clear. Okay, so what happens is that there is a table somewhere in the compiler, and that table, it contains an information of what is the address pointer of the host and what is the address pointer on the device. The reason why we want to have target data regions is because memory copies are really, really expensive. So if I'm going to be copying back and forth the data and never utilizing the memory back in the host, I am going to be wasting cycles just by doing the copy in between one and the other, right? So what I want is to be able to say, copy the data, but if I try to allocate, if I try to reference the data again, because there is some implicit data mapping, or because I do have a data map from, then in that case, I think I have an error here. I don't think this is allowed. This should be a target region here, not the target data. In that case, the idea is that I take advantage of the fact that I created a data region at the beginning and that I already have the values on the device. I do not want to copy the values again. I just want to be able to modify and operate on them again. So in this case, I have a table at the beginning of the target data region. I allocate the address of X, the offset is 0, the size is 4, and I increment a reference. Because it's the first time I increment the reference, I'm going to copy the value, and this is a to from operation, I'm going to copy the value to the device. Then I do X equal 10. Give me 1 second, I'm going to fix this. Sorry about that. I don't want you guys to be confused by this. Of course, it's the one that has. There you go. So again, we begin. So we have the value X in the host, we do the mapping, we put it in the table. The reference is 1, is 0, we increment it by 1, we make the data copy. We go and execute code inside of the target data region. Remember, target data region code is still executed in the host. So what I'm doing is changing the host value here. Then we do a target OMP target map. All we are doing is incrementing the reference, but because the reference is not 0 at the beginning of the target data map, I do not make a copy of that value. That means that this 10 that I have here is not going to be copied over to the device. So I am counting in my head, I am counting reference to understand if there is going to be a memory copy or not. I start in 0, I go to 1, I make a memory copy. I am in 1 here, I go to 2, I do not make a memory copy. That means that this X++ here is going to be executing on the original value of 5, making it a 6. Again, I finish the data region, I decrement the reference, so I go 0, +1, +1, and then at the end I do -1, but because I am not in 0, I'm not going to be making a copy of data into the host. That means that the reference, so the value that I have here, 6, is still different to the value that I have in the host, and that when I go to the host and I'm going to increment the value in the host. And here is what is tricky, is that when I reach the end of the target data map, I am overriding this value of 11 with the value of 6 that I have in the device. And then because I reached the value of 0, I remove the value, the reference from the table, I deallocate the value, and I'm all happy. And what I print here is a 6, right? So if I want to always make the data copy movement, what I need to do is apply a modifier to the map operation that will guarantee that every time I reach there, I make the copy. So in that case, I have 5 in the host, then I have 5 in the device, then I have 10 in the host, but I have an always here. That means that the device is going to go from the device is going to go from 5 to 10 in this memory copy here, and then I'm going to increment it here, increment the host here, and I get 12 here at the end. Okay. Yeah, it gets a little bit tricky. Absolutely. Okay, questions so far? All right, data movement on demand or unstructured data movement. I just go and say, I need the data to be moved. I don't have a beginning and end. I don't have a connection in between when I begin and when I end, right? So how can I do it? I can do it with target enter data, target exit data, right? Each of the 2 operations are completely independent from each other. I can do a target update, or I can use pointers in the host and use the pointer data directly. So in this case, I have a program, I reach this point and I say map to A, and I'm just going to move the data there, right? Then I continue the program and I say map alloc B, and I'm going to allocate B into a device. And then I continue the program and I find a target enter data map from B. This should have been exit data, not enter data. Exit data map from B, then I copy the value back. And then I have exit data map delete, and I delete the data from the device. I'm going to fix that later on. Okay, so just same thing happens with the reference, right? So I increment it by 1, I make the copy, I modify it in the host, I increment it by 1 again, I do not make the copy, I modify it in the host, right? And then I decrement it, I still do not make the copy because the reference is 0, and when I print, I actually print 3 because that is what is in the host, right? So +1, +1, -1, still not 0, so I do not make the copy. This table in your head has to always be clear when you're writing code with data movement, because you have to always be careful if you're actually doing the data movement or not. Okay. Target update, on the other hand, is the contrary of that. It's saying I need to make the update from either the host to the device or the device to host, right? So I'm forcing the operation to actually update one from one to the other. So if I have a target update, I actually make the memory copy. And finally, what we can do is we can use the OpenMP API to have full control over memory allocation. That means it works exactly like a malloc that you do in C, but in this case, you are doing it on the device directly. But when you do so, it is absolutely your responsibility to be able to control the mapping in between one and the other, right? So there is this idea that you will see in the lab that is because there is a malloc that happens in the host, that value of the malloc is going to be a value, the memory operations in that value is going to be pointing to a memory operation, sorry, to a memory location that is in the device already. If you do not specify that that memory location is already in the device, the target operation is going to try to translate that pointer from host to device, and it's going to give you an error at the end. So I have an example of this in the other. Okay, go to the lab 4.1.